by 4, and I think the problem set is currently at up to 138. So if we have any questions on things.
Can you do 134?
Sure. So it says the pH of carbonated water is 3.9 and the pH of household ammonia is 11.9. What are their hydrogen ion concentrations? So I am going to be using the pH formula. Hopefully that's not a big surprise. So that's my pH formula. So for the carbonated water, I'm just going to write that as CH2O as the subscript so I remember. To solve for the concentration of hydrogen ions, I need to first move the negative sign to the other side. So I'll just divide by a -1 or multiply by a -1, whatever your fancy is. So far, so good? Okay. Next thing we need to do is cancel out this log. So what cancels a logarithm? What operation will cancel a logarithm?
The base.
An exponent base. Very good. And which exponent base would I want to use to cancel this particular logarithm?
H.
10. Very good. Why 10? Right. So the common log is just written log with no subscript. And we understand that to be base 10. Well, we had covered it, whether you remembered it or not. It's a fair point. It's come up, and it'll continue to come up, so it's a good one to remember. So at this point, it's calculator time. So I'll just do 10 to the -3.9 on my calculator. Maybe I didn't press the button all the way. Go. So I get 1.26 times 10 to the -4th, or I could write it as 3 zeros and then my 1.26. And the unit here is in molarity, which is moles per liter. So far, so good with that, Grace?
Kind of. Like, where do you get the CH2O?
Well, it asks us to do it for both the carbonated water and the ammonia. So I just put a label on there because I'm going to do the same thing now with ammonia.
If I did, that would be wrong.
No, just me putting a label on there so I remembered which one was which, because I assume I'm going to have to do something with this number in the next parts of this problem, part B or C or whatever. I didn't want to get confused and use the wrong numbers in the wrong spot, so I just stuck a label on the subscript there for mostly just for me, not to get confused. So then we do the same thing, and we say 11.9 equals negative log. And then I need a subscript for ammonia. Now because I'm an extreme nerd, know the chemical formula for an ammonia, and that's going to be shorter lettering than any like AMM or whatever you might want to use, but that's what I'm going to use is NH3, which is the chemical formula for ammonia. Any kind of subscript you want to tack on there just so you remember which one is which would be fine. Now, is this problem any different than the previous one? No, it's like the exact same thing. The only difference is we have an 11.9 instead of a 3.9. So I'm not going to show the work a second time. Can somebody tell me how I'm going to be able to find the final answer?
It's going to be 10 to the 11.9.
Negative 11.9. Very good. We okay with that? That I just kind of like hand waved my way through it because it's like, yo, it's the same work. So I get 1.26 times 10 to the negative 12, or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros, and then the 1.26 mole per liter of my ammonia ions. Part B, it says, how many times greater is the hydrogen ion concentration in the carbonated water than that of the ammonia? So when we say how many times greater, we're just talking about like a division problem. So I'm going to just take the carbonated water concentration, divide by the ammonia concentration. And I'm just going to use my calculator to kind of do that. Fiddlesticks. What did I do? Well, I did exactly what I was trying not to do when I labeled them in the way I wanted to, is I did them in the wrong order. I put the wrong number in the wrong spot. Oh, Mr. Kulik. Well, I Kulik the heck out of that one. So what do we got here? We got 1, 2, 3, 4, 5, 6, 7, 8. 8 zeros and a 1. So we have 100 million times greater. Is that okay there? Okay, I think I counted that right. Let's go back and count it one more time. 1, 2, 3, 4, 5, 6, 7, 8 zeros. Okay. All right. The last question asks, by how many orders of magnitude do the concentrations differ? So when we talk about orders of magnitude, what we're just talking about is powers of 10. So 100 million is 10 with how many zeros after it? 1, 2, 3, 4, 5, 6, 7 is 10 to the 7th. So that's 7 orders of magnitude. No, 8. Sorry. No, I was right.
Can you explain why? You just count 7 or zeros?
Just the exponent is the number of orders of magnitude. So like when we talk about an order of magnitude, you're talking about like a decimal point changing, right? Like if you talk about like between 10 and 20, there's no change in order of magnitude. But 10 and 100 is 1 order of magnitude because the decimal points moved 1 place where the number's hiding. If that makes any sense. That's all we're talking about. Is like how many powers of 10 do they differ by? Grace, does that feel okay?
Yeah, so like, for C, you don't do it for the other.
No, well, because it's asking by how many orders of magnitude do they differ by, right? So you're looking at
Oh,
this number, or you're looking at how much more concentrated is one than the other, and that's going to give you the order of magnitude is the ratio of concentrations. Yeah, sure, no problem. Who's next? Happy to do some more. Can just be general stuff too if there's something we've been doing that you don't really understand, or you're like, yeah, I feel still a little hazy on this. Can we talk about it some more? You can ask about that kind of stuff too. That's fine also. And if you don't have anything, that's okay still too. Like it's not like there's any pressure to like come up with something. But I just, we got time. This tends to be some of these things tend to be conceptually a little bit difficult. So
can you do 136?
sure. So 136 says a cup of coffee has cooled from 92 degrees to 50 degrees after 12 minutes in a room at a constant 22 degrees. So that's the temperature in the room is the 22 degrees. How long will the cup take in order to cool to 30 degrees? So this is like a Newton's law of cooling problem because we're talking about something cooling down. So the formula that we gave you was this. Right, so the T of T is the temperature of the substance at T minutes after removing that from the heat. Tm is the surroundings temperature, like the temperature of the room or whatever. If you're dunking something in cold water, it'd be the temperature of the cold water. It's the temperature of the surrounding medium. T naught is the temperature of the substance when you remove it from the heat. So like in this case, it was the 92 degrees. The K is a constant, but that constant is specific to the substance that you're working with. So like the constant for water would be different than the constant for iron. They're unique for each substance. And T is the little lowercase t is the time that the object has been removed from the heat source. So when I read 136, the thing that I don't have in order to use this formula is K. Right? And nowhere in there do they give me the constant. So my first order of business is to figure out what that constant is. And then I can use that, once I have that, to answer the last part of the question. So I'm going to kind of think about this as two steps. So I'm going to use the part that I've highlighted in yellow to figure out what K is. And then after I know K, I can use that to deal with the green question. Okay. So let's start with the 92. Where is the 92 going to go?
With the, did you say T naught?
Yes, very good. T naught is the temperature of the substance when you remove it from a heat source. Okay. And then where's the 50 degrees going to go? If you're not quite sure, continue reading a little bit after the 50 degrees.
After 12 minutes.
Yeah, so that tells you that the 50 degrees is the T of T, because it's the temperature. Yes, because it's the temperature like 12 minutes after. So that's this value. And then obviously the 12 is the lowercase t. Everybody's okay? So we did that. We put that somewhere. And then that means the 22 degrees must be the TM, right? So far, so good? Okay. To solve this equation now for K, that's going to be our first step. What should I do to solve for K? The first thing I would need to do is nope. So our goal is to eventually get that K by itself, right? The K is located in the exponent. So eventually I'm going to have to use a log, but I'm not ready to do that yet because the exponent part isn't all by itself. So that's going to be my first order of business, is to get that exponent part all by itself. So what do I need to do in order to do that?
Should you distribute it out?
So this is the exponent part, right? So let's get rid of this 22, just like we would a linear equation, right? Like a, A is equal to B plus CX kind of thing. And 92 minus 22 is just 70, so I'm going to just write it that way. Everybody's okay? Next thing I should do is divide by 70. Very good. Again, our goal is just trying to get that exponential piece all by itself. Still doing okay? Next up would be time to cancel that exponent base. So we need to use a log. Very good. Log of what base should I use? Log base E. Why base E? Because it matches the base of the exponential, right? Now, log base E has a special symbol. Do you remember the symbol we use for log base E? That's the ln, is log base E. But if you wrote log base E on your calculator and did log base E on your calculator, it would be okay. Like that's fine. They mean the same thing. So we have natural log of 28 over 70 equals negative 12k. The last step would be to divide by negative 12. Yeah. I'm going to write it as multiplying by the reciprocal, mostly because I don't want to confuse us as to whether that 12 is being divided inside the logarithm or outside the logarithm. When I write it like this, it's super clear that whatever is going on outside of the logarithm, right? And so now it's calculator time. We'll just do negative 1 over 12 times the natural log of 28 divided by 70. So that's my value for k, about 0.0764. So this is like the yellow part that we identified in the problem. Now let's do the green part. So the only thing that's changing here is, so the temperature of the medium, the surroundings are still the same. The temperature that it was removed from the heat source, still the same. The K, we now know. So all that stuff is going to stay, oops. Put the E in there. All that part still is going to stay the same, right? All right, let's go back and examine what we were asked for in that green piece. It says, how long will the cup take in total to cool to 30 degrees Celsius? How long means, what are we solving for? Time, the little t. Okay? And so the 30 degrees then must be our, there's only one spot left we could put it, right? Based on what we filled in, it has to be our T of t. Is that okay? So now we're just solving for t. T is still in the exponent, right? So the steps are going to be the same kind of steps. Exactly right. So we'd want to start by
Moving the 22 to the other side.
yeah, subtracting the 22, moving it to the other side. Very good. And then again, 92 minus 22 is still 70. So I'm just going to simplify that nice and easy in my head. Next step would be to divide by 70. Very good. Okay. Actually, I'm going to write it like that so I can not have to recopy it here. And then what's next? Use the natural log to both sides. Very good. Again, we're using the natural log because the exponent base in question is e. And then my last step would be divide out that negative value for k, right? And again, I'm going to just write it as multiplying by a reciprocal just so it's like super clear when you go back and you look at your work where that number belongs, that it's outside the logarithm. All right, so negative 1 over, and I'm just going to grab my value for k that's still on my screen, times the natural log of 8 over 70. So about 28.4 minutes. Does that feel okay? A lot to do for that, but The nice part is the second step is basically the same exact steps as the first one, so it goes much quicker. Okay. Anybody else? Okie doke. Well, this is good. Like, we knocked out two, reasonably difficult problems from the problem set that you don't have to worry about. We've done them here in class, and there's only 7 of them on there right now, so that's good. You have 2/7 of your way done. Hey, way to go, guys. Look at all the hard work we've done already. Now, I took a long time doing those because I was going, like, very slowly explaining things throughout. Like, they'll probably go faster when you sit down and do them, but there's a reason there's only 7 problems in that part of the problem set, because they take a minute. So what we're going to be talking about in the last section is some applications into the world of finance and banking, which is super exciting, maybe or maybe not, but involves money and things that, like, legitimately as a functioning member of society, you should, like, understand how interest rates work and, like, loans, and these are things that are helpful being a good consumer. So we'll get a little sampling of that right now. Okay? So there's kind of, when we talk about interest, there's really 2 types of interest. And we know what interest is, right? Or no? It's not like things that you find fascinating.
It's like how much, like, the growth of your money can be.
Right, so there's kind of 2 ways that interest gets applied in finance. One is if you're saving or investing money, you're basically being paid by the bank to save your money there, and they'll pay you some interest rate to keep your money in the bank. So some percentage of what you have saved, you're paid out over time. Why is the bank paying you money to keep your money in the bank?
So they can invest it.
Yes, basically they're going to take your money that they're holding on to and loan it to other entities, other people or businesses. And that business is going to take the money from the bank with the agreement that they'll pay it back with some interest. So, like, if I borrow, $10,000, I might say, okay, I'll pay that back over 5 years at 3% interest. So, like, the money that's still outstanding that I owe to the bank, there's like a 3% interest paid onto that. And that's how banks make money, is they pay you a lower interest rate to keep your money saved there, then they sell your money back to someone else in the form of a loan with a higher interest rate on it. Does that make kind of sense? So there's 2 ways that banks use an interest rate. They pay you some interest to keep your money, and then they basically sell your money back out to someone else at a higher interest rate. I know the term selling money seems kind of weird, but that's really what they're doing, right? Okay. So there is 2 types of interest that we'll talk about here. The first is simple interest. So simple interest is based only on the original investment or loan. So in this case, our formula for simple interest is just going to be I equals the present value or the original amount invested or loaned plus or times 1 plus Rn over 100, where R is the interest rate written as a percentage, and N is the number of years in which that investment is made or that loan is made for, whatever. So simple interest. I use PV for present value. That's like the original value for the loan or the investment or whatever. So let's look at an example here. So little. Okay. So assuming we have simple interest, if you invest $2,000 at a 6% interest rate, how much money do you have in the account after 3 years? Again, I didn't put it in the question, but let's assume this is simple interest. Okay. So my simple interest is going to be the present value times 1 plus Rn over 100. What would be the present value in this situation?
Can you scroll up so I can see?
Well, it's just this question right here, right? The PV is the present value. 2,000, right? The initial investment or loan. The R is our interest rate, so that's 6. And N is the number of years, 3. So when I grind that through my calculator, I get 360. Let's just do it real quick. Oh, I see. Okay. All right. So this is just a mistake on here. Okay. I need to go back and make a little revision here. So hold on to your butts here, guys. We should say this is FV for future value, where the I, well, let's just leave that as I there, is just PV times Rn over 100. Or really, we can think of this as just future value minus present value. So the simple interest is this, and this would be to calculate the interest is the yellow. But if you actually want to do a problem where you're asking like how much money is the account worth, we would use the future value version, right? So if we asked how much interest was earned, we can use the one on the right. If you're asking for the account value, use the one on the left. That needs a revision in the notes because it's not not clear and not well articulated. So these should be FVs here. And this would imply that you earned $360 in interest. Does that feel okay to everybody? My apologies for kind of making a mess out of that. Okay. For the record, no institutions really do simple interest, right? Because why would we continue paying you interest on the principal investment if you've like made more money over the course of that term? I'd want my interest to reflect the more money or be paid on like the current account value, which could potentially be more than it was previously. Or if I'm the bank, I don't want to pay you the same interest when you had $2,000 if you've taken $1,000 out now, right? If you've taken some of your money back, I don't want to continue paying you the same interest. So nobody really does interest that way, but it's like the naive kind of first step. The other type of interest, the one that basically everyone uses, is compound interest. And that is where the interest rate is always calculated using the current of account value at that moment. So again, FV is future value. That would be what the account or loan is worth in the future. PV is the present value. That's like the initial amount that you borrowed or was in your account. R is our interest rate as a decimal. K is the number of compounds per year. And N is, again, the number of years. So those of you that have you guys have bank accounts, right? I don't remember, like, as a teenager when I really had a bank account with anything in it. But probably by this age, I probably had a part-time job and had a bank account. Have you noticed that you get interest paid more than once a year in your bank account? Probably not looking at your statements. I probably wasn't as a teenager. Typically, you get paid interest rate like 4 times a year. I think most banks pay interest out like quarterly. So when it talks about the number of compounds per year, it'll usually say like blah, 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 interest compounded quarterly. That would mean like 4 times per year. Maybe it was compounded monthly, be 12 times per year. It could be compounded semi-annually, which would be like twice a year, or like compounded yearly, which is just one time per year, or compounded daily, 365 times a year. You know, you kind of get the idea. Or weekly, how many weeks are in a year?
52.
Good job, guys. These are like facts that I just take for granted that everybody knows, and I find out after doing this long enough that like a third of people are like, I don't know how many weeks are in a year. It's like, what planet have you been living on? Because that would be a good excuse, because the number of weeks in like a Martian year different than number of weeks in like an Earth year. So if you're like, yo, I'm from Venus, sorry, I haven't figured it out yet. It's like, oh, good excuse. But I haven't met many Venetians in my teaching career, so, you know, that's going to be a tough sell. Be like, I need to see some more proof of that. Can you show me your spaceship? It's like, well, I actually don't have a spaceship because I just, you know, like fold space. So it's basically like teleporting. I'd be like, oh, that's pretty neat. How does that really work? It's like, well, I can't tell you because we're actually going to try to take over your civilization. And if I divulge that information, you know, it's like puts us at a strategic disadvantage. And it'd be like, I am going to end this conversation right now because I'm getting a little weirded out.
It would be a hard day.
Yeah.
Yeah. Lots of content.
All right. So same question, but this time we're going to use compound interest. Notice in the phrasing of the question, it says compounded annually. That's the new piece in there. That's just telling us that the K is 1. This is just what we got done talking about. Okay. So again, compound interest has a new formula. Oops. So the present value still the 2000. The R is still the 6. The K is 1. And the N is still 3. Now this is presuming that I haven't withdrawn any money. Everybody's okay with that? I've just put that 2000 in there and left it to rot for 3 years. Because apparently I don't have any real bills or anything. What do I notice though? 2,382.03. Compare that to the simple interest. Was it more or less? More, like 22 bucks more, right? Why is it? Why are we getting more money?
Because it's like
Because after year 1,
it takes the new number.
I have 2120 in there, and the next year I make my interest off of that, and the next year I make my interest off of that number. So there's always a little bit more in my account every year. So like I'm getting a little bit more interest paid out each time. Now, in this example, over 3 years, 22 bucks, over 3 years, 22 bucks is not much to write home about. Let's just illustrate what the difference would be, though, if we went over 30 years. Okay? So 2,000 times 1 plus 6 over 10 to the 30. Oh, 6 over 100. I was like, it's like, that is a bonkers number. What did I do wrong there? One more zero there. Okay, so there I have $11,000 and change with compound interest. If I do this with simple, woof! Now that's a difference, right? So what's going on here? Why are we seeing such a dramatic difference between simple and compound interests?
It's exponential.
Yeah, so the simple interest is like a linear curve. So if I, like your simple interest is just doing this. Your compound interest is doing this. So the further you go along the x-axis, like, woo, buddy, you're getting a lot more money. And in fact, I think in this situation, it would actually be, if the interest rates are, everything else is identical, it's going to be kind of more like that, where you're never going to have the simple interest be better than the compound interest if they're at the same interest rate with the same number of compounds per year. So it'll be more like that. But compound interest is a beautiful, beautiful money-making, like a beautiful money-making Duderowski here. What I want to take a minute here and now look at is how much difference like that number of compounds per year makes. Right? So let's just look at k equal 1 to, let's see. So we have annually, semi-annually, quarterly, monthly, weekly, and then like daily, I think would probably be sufficient. Yeah. So let's go back and grab, I'll just redo it. It's not worth grabbing. So I have R over 1 times 100 to the 1 times 3. So there's the 2382 we saw initially. Now, if I change the number of compounds per year, do you expect that number to be bigger or smaller? Bigger. Do you think it's going to make going from 1 compound to 2 compounds, do you think that's going to make a lot of difference or little difference?
A little.
Just a little. And it'd make $6 a difference. Why so little difference? Because you're only getting paid like half of your interest, on like 6-1, and then you're getting the other half of your interest paid on, 12-1. But there is a difference because the 6-1 interest is now part of the interest at 12, or part of your account value at 12-1. So it's like makes a difference, but just a little difference because the interest rate is still kind of staying the same. Okay. Let's see if we change that from 2 to 4. So we picked up $6. Only got $3 that time. All right, well, let's change that out to 12. Do you think this is going to make a big difference? So what do we pick up here? $2. Still a lot more than it was with 1 compound, right? But like we did 3 times the number of compounds and only picked up $2. It's kind of disappointing. Well, what if we do 52 is next? It's like 5 times the number of compounds. This is going to have to make a big difference, right? Less than $1. 365. Big deal or no deal? Yeah, not much of a difference. Couple of cents, a quarter or something. So that number of compounds per year we're seeing does make a difference, but like it can only help you so much. Like it gets bigger and bigger and bigger. You know, like, ooh, what can we do? Can only do so much. So that's not a great indicator of like how good of a deal you're getting. More important would be the interest rate itself. That's going to be a much better indicator. Notice here I haven't like really been writing much down because we've just been doing everything on the calculator. It'll be kind of the same way in the homework, where this is going to be a very calculator heavy section. Okay, so this is same kind of situation. Mara has $1,000, places it in a savings account with 6% interest compounded monthly. How long will it take before Martha has $4,000? Okay, well, I heard compounded and interest when I read this, so like right away, I know I'm going to be using my compound interest formula. Where does the 1,000 go? That's the present value. Very good. And then 6% is my R. And compounded monthly tells me the K is 12. Very good. And the question asks how long, so what are we going to be solving for? Oh, I'm sorry, that's supposed to be the N there. I always want to call it T because in all the other formulas, time is T. I don't know why we've used N for time. It drives me bonkers. And then the 4,000 must be the future value. Okay, so what are we really solving for here? An exponential equation, right? So the first step to do this would be, great, divide both sides by 1,000. Okay. And now this is a decimal, right? But I'm not going to turn it into a decimal. I'm just going to use, you know, so I'm going to just leave like, when I do my log, I'm just going to write it like this because it's probably a decimal that I don't want to mess with the rounding on it. I'm just going to like, that's the way I'm going to type it in my calculator. That's the way I'm going to write in my paper because I just, you know, like don't want to hassle with it. I'm just going to write that because I'm sick of rewriting that again. Does that feel okay to you guys? Really the same solving steps we've been using now for a couple of chapters. So I'll start by pressing the math button and going down and retrieving the log base command. Oops. Forgot to write the 1/12. And then down in the subscript, I can just write this exactly as it looks like on my sheet of paper. And it gets about 23.16 years. Everybody okay with that? And really any problem where we're asking to solve for the time, like the how long problem, basically those are the steps, right? Doesn't matter any other the conditions, like some of the numbers will change, but the steps would all be the same for that kind of a problem. Another kind of problem we can have says Gwen has $600 to place in a savings account. What annual interest rate would she need if it's compounded weekly if she were to have exactly $1,500 in 10 years? So again, I heard compound and interest in here, so I know I'm going to be using my compound interest formula. Where does the 600 go? That's the present value. Very good. And then it asks what annual interest rate. So what will we be solving for here? R. Great. And then we have compounded weekly, so the K is 52. Nobody from Venus in this class. And then the 1,500 is the future value. And the 10 years is the end. We feel okay here? Now notice, where is the variable here? It's in the base of the exponential. It's not in the exponent. So do we need a log to solve this? No, because we're going to have to cancel the exponent, not the base of the exponent. All right, just wanted to point that out. First step, though, is divide by the 600. Excellent. And I'll reduce that a little bit. I don't care about reducing it all the way, but like I'll knock those zeros off. Everybody so far so good? How am I going to cancel out? What do I have to cancel next in order to get to the R? The exponent. Great. What operation cancels an exponent? Well, let's simplify this. What if I just had like 4 is equal to x squared? What would I use to solve this? Anybody? Just as a hypothetical? If I wanted to solve 4 is equal to x squared, what would I do? Anybody at all? Square root both sides. Yeah. So what if I had 4 is equal to x cubed? Cube root both sides. So if I have this problem over here, what am I going to use? A 520th root. Is that okay with everybody?
Yeah.
I mean, It's like, it's a weird looking radical, but like, okay. Okay. Next step would be to subtract the 1.
Yeah, that'd be good.
All right. So I'm going to write it like -1 plus. And I am doing that just so I don't confuse myself as to whether that -1 is happening under the radical or outside the radical. When I go back to type this into my calculator in a moment. And then my last step would be to
You gotta get rid of the 5.
so multiply both sides by 5,200.
Yeah.
So remember, when I do that, I have to do it to both sides. So I'm going to use like a parenthesis there.
Can I borrow a calculator? My die.
Sure. Just make sure I'm giving you one with some battery in it. That one's not doing great. Or that one's doing very great. I think there'll probably be enough for you, but I just... This one's doing pretty good.
Sweet.
Oh boy.
I'll bring it back after.
Thank you. If you don't, I'll come find you. All right. So then the last thing I just need to do is type this in. So 5,200 times, and I have -1 plus. And then to do a 520th root, I'll type 520. I'll press the math button, and then the option 5 allows me to pick any index I want, so it'll automatically move the 520 there into the index. You could pick the other one first and then type the 520 in. It doesn't matter which way you do that. Okay. So I do that and I get 9.17%. This looks like a good place to stop. Let's stop here for today. Let me go look at where we can go to now. We can go to 155.